we will start this lecture 20 with a simple thought process. A mighty flame emanates from a tiny spark. If you look at, we are basically discussing about the chemistry of combustion, right. And in the process we looked at law of mass action, then we moved into the collision theory to find out reaction rate. If you recall, reaction rate is proportional to not only the concentration of the species, participating species, and also it will be dependent on the activation energy and also the pre-exponential factor which comes from the collision theory. And that reaction rate coefficient which is determined from the collision theory is based on what you call is known as the Arrhenius law, right. And what we will do, we will take an example today how to use this Arrhenius law, and also whether we can determine the activation energy by conducting experiment or not, that we will illustrate through this example. And this example is basically a vessel, which contains 10 power to minus 6 mole per centimeter cube of nitrogen dioxide at 650 Kelvin, right. If you look at it, is basically isothermal reaction which is decomposed into the following reaction, that is 2NO2 goes to 2NO plus O2. Keep in mind that this is in one direction, the reaction can also come in the backward direction as well. This is the forward direction, backward direction, but we are considering at this moment only the forward direction. We need to determine the reaction rate of NO2 assuming Kf to be 770 centimeter cube per mole second, and we need to also determine the activation energy if this reaction rate is obtained as the 400 centimeter cube mole per second at another temperature, that is 600 Kelvin, right. So, there are two parts. One is that we need to determine the reaction rate of NO2, where Kf is given. If Kf is given, then is it possible we can find it out, right. We will have to basically apply the law of mass action. Kf is known to you, and then we can determine what is the reaction. Let us do that. That is a simple part, and of course, here we are assuming the reaction to be elementary in nature. What is the meaning of elementary reaction? That we will try to discuss maybe after this example, but keep in mind that the law of what you call the Arrhenius form of equation is valid only for the elementary reaction, but however, we will be using for the global reaction as well. And law of mass action also, right, is also valid for the elementary reaction only. Okay. So, therefore, whenever we are applying the law of mass action, we should keep in mind that reaction must be elementary, but you must know what is elementary reaction and how it is different from the other reaction, and how many kinds of elementary reaction one can think of. Those things we will learn, but before that let us look at this problem. So, reaction rate is equal to minus half dCNO2 divided by dC. What is it saying? This is a rate of concentration of NO2 with respect to time. Of course, rate when I saying it is means it is time, and of course, the minus sign is there because it is being decomposed, therefore, it is minus, and half of course, I have taken because 2NO2 is participating, which is equal to Kf, that is reaction coefficient, right, reaction rate coefficient, and CNO2 square, right. Why this square comes into picture? Because the coefficient in this reaction is 2, and it is an elementary reaction. So, that is stoichiometric coefficient, right. So, therefore, it comes as a square. And then what we will do? Because concentration is given, this is your concentration of NO2, and this is known you just substitute those values and get the answer, which is very simple. That is at 650 Kelvin, that is reaction rate is equal to minus half dCnO2 by dt, and you just substitute these values for Kf from here, and then CnO2 square, you will get this value 0.77 into 10 power to minus 9 mole per centimeter cube. It is a very small quantities if you look at, right. And activation energy for this reaction can be estimated by knowing the specific reaction rate or the reaction rate coefficient, both are same at two different temperature. So, one is 650, other is of course, the 600 Kelvin. So, we must know those values and Kf is known. So, we can determine, that is at T1 it will be ln K1 is equal to ln A minus E by T1 RU. How it is coming? Because we know that K1 is equal to A E by R T1, right. Of course, this is RU, right. So, if I take both the side log, then naturally get ln K1 is equal to ln A minus E divided by T1 RU. Similarly, I will do for the at the temperature T2, that is ln K2 is equal to ln A minus E divided by T2 RU. RU is the universal gas constant, right. What I will do? I will just say like equation 1 minus equation like equation A minus equation B will give what? If I just say this is minus and it cancel it out, what will happen? So, this become minus, this become minus, this become plus. So, this will cancel it out, right. What I will get? I will get ln K1 minus ln K2 is equal to E by R T2 minus E by T1 RE, right. I can get that, and we will simplify this and get those expression, because now E is both are same. So, we need to determine E from this equation, and I know K1 is known, K2 is known, and T1 is known, T2 is known, RU is of course the same. So, you can very easily determine what will be E. Let us look at that. That is E become RU T1 T2 divided by T1 minus T2 ln K1 by K2. So, all these are known K1, K2, T1, T2 RU. So, you just substitute those values and you will get, that is 42.5 kilojoule per mole. Keep in mind that the unit must be same, this is very important, otherwise it will be land in some different values. So, what we have learned from here? We have learned that activation energy can be easily estimated once experimental data is available. Of course, most of the experiments are conducted under isothermal conditions, because where you can maintain temperature. We have seen that it is the reaction rate is strongly dependent on the temperature. So, therefore, it is a very minor change. In this example, it is only the 50 Kelvin difference, and it is, if you look at the reaction rate has been changed. If you look at the specific reaction rate is changing from 770 to 400, only 50 Kelvin difference. So, therefore, it is very important to conduct in the reaction in the isothermal condition, right. Generally, most of the data whatever we get, we use isothermal unless otherwise stated, and of course, in some small reaction. Why it is so sensitive, this Kf or K, the specific reaction rate constant to temperature in this example, right? Why? Or is it true only for this example, or it is different for different reaction? Because it goes exponential, right? And if you remember, I had shown you how this reaction rate will be changing with respect to the temperature. For example, if I plot it here, reaction rate with the temperature, if you look at it in the beginning, it will be reaction rate will be going like this, and then it will be coming like that. Now, it increases at a very rapid rate whenever it will be going towards high temperature, but why it is going down here? Did you think about it? Last time I had discussed this, but I did not discuss about in detail, but I thought you will be thinking and asking me a question, why it is so? Can anybody tell me?
Dissociation of molecules.
Dissociation always will be occurring or some reaction will be occurring, but why it is going up? Because it is exponential. We have seen that k is equal to a power t e by r t. And why there will not be any reaction which will be there in this temperature? Because the activation energy like may not be having that high. So, it will be remaining, I have exaggerated a little bit, it will be remaining almost constant in the low temperature, and then it will suddenly going up, right. But why it will go up? Because it is having activation, it will go up, but why it will go down? Because whatever the participating species is there, it will getting consumed, and if concentration is not there, if you look at reaction rate will be k into C of A, C B, or maybe 1 or 2 something. If I look at C A plus B is going to the D, or if I am saying C, if I am saying that A is reacting is going to the C, right. So, this will be C A C B, right. Okay. So, therefore, this reaction rate, if C A is coming to 0, what will happen to the reaction rate? Then it will be coming to the 0 here, even though temperature is higher. Are you getting my point? Similarly, if C B is 0 or C B is very small, or one of them is 0, then you will come to this, even though temperature is very high, right. Is that clear? I was thinking you will think about it, and if you will not get the way, you can ask me, right. Okay. So, let us now get into elementary reaction. So, if you look at what do we call it elementary, if the reaction occurs successfully at a molecular level, the reaction is termed as elementary. In this example, if OH is reacting with a hydrogen molecule, it is going to water and the H, right. If you look at water is a stable molecule, hydrogen also a stable molecule. What about OH? Is it stable? What do you mean by stable? And this OH or the H, what we call is a radical. These are very reactive in nature, their lifetime will be very small, and it will be going and reacting, as we have discussed already about the molecules being collided. As a result, there will be breaking of bonds, old bonds, and forming of new bonds, right. So, therefore, these reactions where there will be molecules or even atoms are involved in that, and some of the like radicals are formed, right, then we call those as the elementary reactions, right. And these elementary reactions will be dependent on what? It will be dependent on molecularity. But what is the molecularity then? That means number of molecules will be participating in a reaction will determine the molecularity of a reaction, right. That means, as I told, number of molecules or atoms participating in reactant in each reaction leading to a product. In this example, OH is reacting with hydrogen going to the water and H. So, if you look at the molecules are participating here and it is going to a product. Product means it need not to be stable alone, it can be any other thing, right. That means there is a change. So, based on this molecularity, right, in this reaction, if you look at the two are participating OH and hydrogen, therefore, we call it a bimolecular reaction. Similarly, if it is a single molecule and it is decomposed, then we call it as a unimolecular reaction. So, the reaction can be broadly divided into 3 categories. It need not to be 3, even 4 also, but they are 4 molecules coming together and reacting are less likely to happen in nature, therefore, that is not being considered. However, nobody can rule it out. Okay. So, therefore, the reaction can be based on this molecularity will divide into 3 categories: unimolecular reaction, N2O5 is decomposed into 2 N2O5 plus O2. That is because one molecule nitrogen pentoxide is being decomposed. So, therefore, it is a unimolecular reaction. But if I consider the backward reaction, can it be unimolecular? Backward reaction means N2O4 is reacting with oxygen is going to the N2O5. We have seen anything can happen, either reaction can be forward, reaction can be backward as well. So, at that time it is not unimolecular. Only for the forward reaction in this example is known as unimolecular reaction. Bimolecular reaction, where two molecules are participating, or rather two reactants like CO2 and hydrogen, it is going to the water and carbon monoxide, right, and that is known as bimolecular. Fortunately, both the forward and the backward are bimolecular in this example, right. Similarly, trimolecular reactions is where three molecules are being participated, like CO2O plus M is going to the CO2 plus M. M is known as a third body reactions. Third body reaction means it will be not participating actively in the reaction, but his presence will be required. For example, a referee, in the games, of course, the referee role is different, but he must be there to any games to be conducted, right, but he won't play in the games, right, but his presence is required. And what is this M can be in real example? M can be anything, it is a stable, it is basically stable species like water, oxygen, right, hydrogen or carbon dioxide, those are basically stable species. That means which won't be, unless otherwise large amount of energy will be available, which is beyond their activation energy to decompose. But keep in mind that each reaction will be having certain activation energy. Unless otherwise the reaction or the participating species possess that amount of energy, beyond this threshold value of activation energy, reaction won't occur. So, therefore, those are stable species. Of course, one may be stable species for one reaction, but it need not to be stable species for the other reaction, it may be participating. So, therefore, these are known as third body reactions, right, and third body reaction will be more important in case of higher pressure. When the reaction is occurring at higher pressure, third body reaction is very important. So, now when you talk about molecularity, but there is another one we talk about, order of reaction. Question arises, what do you mean by order of reaction, right? The order of mathematical equation like algebraic equation, PD, partial differential equation, ODEs, like order of equation we know, but similarly we need to understand what is the order of reaction, which you must be knowing, I guess. So, that means it will dictate basically how many species are being participated, and not only that, that is of course you can say that number of molecularity, but it will be depending on the number of molecules atom whose concentration would determine the reaction rate. That means it basically comes from the law of mass action, right. If I take this example of N2O5, it is decomposed to N2O4 plus O2. If I look at this forward reaction alone, then what will be the reaction rate? Reaction rate will be dCN2O5 dt is equal to minus KFCN2O5. In this case, what will be the order of reaction? Can anybody tell me? It will be only first order of reaction, right. It is a decomposed reaction, so therefore, it will be fast. But if I consider the backward reaction, then what it would be? It will be 3 basically, right, not 2. So, we will take some example to reinforce these ideas of order of reaction. As I told that whenever the first order reaction will be there, then it will be one need to consider only one concentration kind of things, coefficient of the participating species will be 1. In the example of hydrogen going to the 2H, in this case reaction rate is basically dCS2 divided by dt is equal to Kf CS2. Keep in mind this minus negative sign because it is decomposed. So, it will be half dCH by dt, right. I can this I have put other way around, right, because CH. So, therefore, 1 half comes into picture, right, and if you look at I can write down KFCS2, and this is from the basically law of mass action you can say. And the examples of first order reaction, of course, any decomposition reactions like O2 is going to 2O, N2 is going to 2NO2 plus half O2 is basically first order reaction, provided you are considering only the forward reaction, that means in this direction. I can say this is forward reaction, right, Kf. Backward reaction, of course, it need not to be, it will not be, right, in this example. So, similarly, second order reaction, let us consider a order of second order bimolecular reaction, hydrogen reacting with I2 iodine going to 2HI, right. So, the reaction rate you can write down dCS2 dt minus KFCS2 CI2, right. In this case, there are two concentration, right, which will be determined what will be the reaction rate. One is hydrogen, other is I2 iodine. So, therefore, it will be a second order reaction. And there are several examples. If you look at lot of reactions which are involved in combustion, particularly second order reaction, some of the example I have given, and OH plus hydrogen going to the water plus H, O plus S2 going to the OH plus H, and H plus O2 going to OH plus O. So, there are several reactions which will be occurring even in hydrocarbon, hydrogen oxygen systems, all those are important. These are second order reactions, right. So, and let us look at third order reaction, trimolecular 2NO plus O2 going to the 2NO2. We are considering only forward reaction in this example. So, therefore, the reaction rate will be dCNO2 will be dt is KFCNO2 square and CO2. And if you look at here, there is no negative sign because NO2 is being formed and we are considering other way around, right. So, therefore, if you look at this is basically the what you call the third order reactions, right, because it is coming from NO and O2. So, therefore, there is no negative sign. So, reaction rate proportional to third power of the concentration of participating species. So, therefore, we call it a third reaction. Some of the example which third order reactions which occur in combustion, I have shown here HO plus O and third body, that M is going to OS2 plus M, H plus H plus H, that means it is very less likely to occur, but also people say that it is occurring. That means H atom has to come through together and collided and form a hydrogen and H, and 2NO plus O2 going to the 2NO2, right. And if you look at all these forward reactions are third order nature, whereas the reverse reaction need not to. Okay. So, these are basically the reaction kind of reaction rates which is governed by the order of reaction, right, and which I am not going to discuss further, but their concentration with respect to time can be varied differently for different order of reactions. If some of you are interested, you can refer to standard books on combustion, and of course, you can refer my book Fundamental of Combustion. So, now let us look at the chain reactions, which is very important. Like, what do you mean by chain reaction? Is it really in combustion chain reaction occur? Certainly yes, because if you look at all the reactions are occurring in chain manner, right. Chain in the sense you initiate something, right, and then something will be propagating. Like, for example, if you look at like if you look at a family, suppose a father and mother will produce a kid, and then that kid will be producing another kid, it will be go on, right. So, it will be terminated, of course, one person will die, it terminated of this thing. So, it goes on, that is a chain. So, whole nature is a chain of actions. Similarly, chemical reaction is a part of nature, therefore, it is chain of action will be taking place. So, therefore, chain reaction will be there. So, in the reality, combustion process involves several reactions, as I have told, and it is not that methane is reacting with oxygen going to the carbon dioxide and water. In enormous or numerous reactions will be taking place between these steps, which is global in nature. So, overall stoichiometric chemical reaction is unlikely to occur in nature. I have told several times, because lot of people believe from their childhood, from their earlier studies, that this is the reaction which occur. In order to eliminate, in order to remove that bogus idea of that is occurring, I am repeating several times. So, that is nature never occurs, is just a model, and elementary reaction can be classified into, elementary means basically chain reactions which will be occurring, into 4 categories. One is chain initiating, that means initiation will occur. Initiation is very important, we do, like you people may not be knowing, in earlier our systems, ancestors were students are being initiated, right. How they are initiated? Initiated by the teacher to start their life, to learn, and they start learning and again teaching, and then it goes on. So, chain branching, of course, they will go and start some another school, thought of schools, and then chain carrying, some of them ideas they carry forward in their life, and chain terminating, some of the chain will be terminated. So, that we will take one by one, like chain initiating. If you look at, if I consider the oxygen O reacting with hydrogen molecule, and both are stable species, keep in mind, and in this case what is happening, that means one oxygen molecule is coming and colliding with another hydrogen molecule. As a result, the hydrogen is being broken, but oxygen remains. Of course, other way around it can occur depending on the prevailing situation, because all are probabilities, all are depend upon the what temperature, what pressure, what is concentration, all those are available. So, in this case what is happening, these are radicals, radicals which are very important to carry forward the reactions, because these are very energetic atoms, molecules, right. So, therefore, this will be chain carrying. So, going to the oxygen, right. So, this is basically initiation, the stable, and you make the stable to unstable and converting into the carrying forward lot of energy. So, that is chain initiating reaction, and chain branching, where ratio of number of free radicals in the product to reactant will be greater than 1, then only we call it as a chain branching. For example, O2 is reacting with the H, is another radical going to OH plus O. In the product, how many radicals are there? 2. In the reactant side, it is 1. So, 2 divided by 1, so therefore, this ratio is greater than 1, right, kind of thing, because 2 is to 1, 2 is to 1 is 2. So, is greater than 1, therefore, this chain branching reaction. So, chain carrying, where the ratio of number of free radicals in the product to the reactant is equal to 1. That means, there is nothing is happening, but the process is going on, like it's I give an example, a son, suppose he is taken over the business of a person, he is just managing whatever the profit he was having, but he is not increasing, that means he is carrying forward, but he is not branching, in this example. So, that means, in this example hydrogen reacting with OH going to the water, and H, if you look at the right hand side, H is 1 radical, in the left hand side only 1 radicals, right, and both are of course other 2 are stable species, right. So, therefore, this is known as chain carrying reaction, and chain terminating where the ratio of number of free radical in the product to the reactant is less than 1. That means, you are basically reducing the number of radicals. When you are doing that, you call it chain terminating, because it cannot carry forward the successful reactions, because the radicals are one which make the reaction to carry forward, right. So, it is basically terminated. Hydrogen is reacting with O plus another, of course, the third body is going to water plus M. M, of course, third body means is stable for that particular reaction, right, and water is already stable. There is no radical in this case, of course, in this example, right, but there in some example it may be there might be a radical in the product, but those number of radicals will be less than that of the number of radicals in the reactant. So, therefore, that can be considered as a chain terminating reaction. So, these reaction will be going on, and then only varieties of things will be happening. So, now what we have seen is basically elementary reaction which will be occurring in nature, but we will be more interested in global kinetics or the global reaction, because it is not easy to really handle so many chemical reactions, particularly when we are trying to model something, right, because those as I go along I will show you, or even the second order reaction, third order reactions and other things, those are non-linear in nature, right. You might have looked at reaction rate, it is dependent on temperature, it is also dependent on concentration, right. If I look at the equation, then you need to solve both the concentration and temperature, both are dependent. So, it is a quite non-linear in nature. So, therefore, to solve those is quite difficult, right. So, and in practical situation, it is difficult to use multi-step chemistry models in engineering application. For example, like combustion process in gas turbine, or you can think of in rocket engines, or any other engine, even in internal combustion engine. Is quite difficult, because in several number of species which will be participating. So, therefore, we need to look at elementary reaction or global kinetics, where we will look at 1 mole of methane is reacting with 2 moles of oxygen going to the product CO2 and water, right. It is a very simple global reaction. In nature is not occurring, but we are assuming it as a model and looking at it. So, when you look at this, whether of course, I have already emphasized this thing, whether this reaction occurs in nature or not, certainly no, it can never occur, but however, we will be interested in overall reaction rate, that is dCH by dt to A e power to the minus e by RUT, of course, C CH for M and CO to N. So, these M and N, these are coefficient which are to be determined, right, by some mathematical tools, and so also the activation energy E and pre-exponential factor A. So, those values will be available by doing some kind of a mathematical model, such that it can replicate the heat release profile, right, because we are interested to how much heat being released. And if it could manage to do that with this global, you will be happy, but however, there is a lot of problem associated with it as well. So, therefore, it is having limitation, and maybe when more computers and other things will be developed, or maybe some other means, maybe we can use elementary reactions in modeling. Even people have started using the brute force of computers. So, this is about methane, but we look at global kinetic scheme of an arbitrary hydrocarbon CXHY, which we have already discussed earlier. It can be C1H4, right, it is methane. If X is 1, Y is 4. Similarly, if X is 2 and H is 6, it will be ethane, propane, butane, like that you can go on. So, if I take this reaction arbitrary hydrocarbon CXHY plus X plus Y by 4 in the bracket, moles of oxygen reacting, giving rise to product of X CO2 plus Y by 2 water, right. for that reaction you can write down basically CXHY dt and minus AFE power to CXY m and n. Of course, these values m and n and e, all those values must be known to you to use it. Okay. So, those values I am not going to discuss, it is there in my book. So, you can use those values. So, let us look at a multi-step reaction mechanism, because I felt that let us look at what do you mean by that, right. And because you may not have a feel what it is, I will just show you a very simple model, right, and which looks to be quite complex in nature, but if you look at this is only maybe around 14 species kind of things and then 40 reaction you can think of, right. But however, this is not adequate to model the methane air chemistry, which is the simplest hydrocarbon, right. For example, I will just give you for example, CH4 is can react react with H or can be O or OH, it can go to CS3 and several other products. Similarly, CS3 can react with O, it can go to CS2, CS2 can be collided with stable species M, O, OH, go to CHO, several others products I am not saying what will be. CHO again maybe react with MO2OH and going to CO, and CS3 can be colliding with CS3 going to C2H6, there is a possibilities. Similarly, CS3 can react with H, like CS3 it can go to C2H and some others. Similarly, C2H can go back react with H go into the CS3, there all permutation combination will be goes on, and similarly C2H is reacting with H going to C2H and some other molecule, C2H can react with H and OH going to CS3, CS2O, CHO, so on so forth. So, if you look at it is goes on and then you can get CO, you can get from CO from some other channel, there are several channels which will be going on. The way our society works, like because we do work in a similar fashion, For example, you may be an engineer, but you may take interest in your family, it may take interest in some other thing, maybe literature, you will be doing interacting, lot of things goes on natural way, right. So, the reactions what I am showing you is a very simple thing, and what it is having a 14 species and 40 forward reaction and 40 backward reaction. I am going to show you that 40 reactions for a methane, right. And if you look at this is the kinetic data and Kf, and for AF is your pre-exponential factor, this is your AF, and Tm these are the coefficient m, and this is E is your activation energy. These data are obtained, right, to be obtained from various reaction, various experiments, of course, what are the error involved in it and what are those things. So, and this has to be solved, that means if you look at like number of species is 14 in this case, right, and number of reaction is 40, and backward reaction also to be considered, that is being considered from the equilibrium chemistry, right, which I do not want to discuss further because it will be quite complex. And this is being used in what you call combustion modeling, and this chemistry cannot work for the rich mixtures. For example, if it can work well for the lean mixtures, like when fuel air ratio is less than stoichiometric ratio, right, but it cannot work for the this thing. So, for that you need to go for more number of species, maybe 33, 32 species are required, minimum bare required, and go for something maybe 400, 500 reactions, right, then only you can get some meaningful result, otherwise no. So, what we have seen till now is about kinetics and other things, but what are the modes of combustion which will be taking place in a combustion system, right. What are the things? Let us look at it. Is basically a very bird's eye view I am giving. One is flame mode. Flame means you have seen, flame is a part of our life, right. You have seen flame, yes or no, right. There are various kinds of flame you might have seen, but whether you identify that or not, but flame can be broadly divided into premix flame and diffusion flame, right. Okay. And there is of course, people nowadays talking about another flame known as partially premix flame, which I have not included here, but however, it is on the research state people are talking about. Flameless mode, one of them is smoldering. Do you know what is smoldering? Like some of you might be, might not be smoking as well, right, or smoking, but that when you burn that cigarette, you get something red color you can see, which is propagating, right. So, that is nothing but a smoldering. You might have seen some kind of a dry leaves being burned, but there is no flame, but it is still burning, right. That is known as smoldering combustion, right. I will not be discussing much about that, because that is quite complex in nature, and of course, similar thing might be occurring in your solid propellant combustion as well, but we will not be discussing about it. And what we will be discussing about premix flame and diffusion flame, right. Now, what do we mean by premix flame? Where fuel and oxidizer are mixed before actual combustion takes place, we call premix flame. And examples you people are aware, that is a Bunsen burner, and of course, LPG stove that you use in your kitchen for cooking food is an example of premix flame, right. And similarly, for the diffusion flame can be defined as fuel and oxidizer are mixed in region where chemical reaction takes place. That is a diffusion flame. What are the example? Basically, your candle flame, your wick flame, and any natural flame is basically diffusion flame. Unnatural flame, man-made flame is basically premix flame, right. That I can say very layman concept. So, this flame, even the combustion, can be divided into two categories. One is laminar flame, other is turbulent flame, based on the flow characteristics. And keep in mind, we will be restricting our discussion to the laminar flame only, and or laminar flame based combustion, although the practical flames are turbulent in nature, right. How we will go and do that is of course a not easy task, but however, there is a way to go talk about turbulent flame in terms of laminar flame characteristics, right. So, if you look at what we have done is basically simplified and trying to understand fundamentals involved in that. But why flame we need to look at is a question, right. Why it is important? Without flame, there will be combustion as well, right. Why you need to look at it? And what is a flame, by the way? We are talking about flame, but what is a flame? Can anybody define it? You can think of a special domain in which rapid chemical reaction, of course exothermic in nature overall way, taking place while emitting light, right. Of course, there is some kind of flame which need not to emit light, right. Do you know any example? The combustion will be taking place and flame will be there, but it is not visible. Is it possible? What is that then? If it is possible, can you give an example? Actually, it is possible, but that depends upon the kind of fuel and oxidizer you are using, particularly hydrogen and air, of course, clean air, it can be, turns out to be very, very faint color, which you cannot really see unless it is dark, okay. In the daytime you can't really see. And premix flame, as I told earlier, that fuel and oxidizer mixed well at the molecular level before combustion takes place, right. But question is it premix flame possible, only when the constituents fuel and oxidizer are in gaseous state, or is it possible in the liquid state, or is it possible premix flame in the solid state, right. I will just leave that question for you people to think about. As you go along, we will see. And examples of premix flame I have already given: Bunsen burner, LPG domestic burners, and what about your aerospace applications? We can model as a basically what you call the SI engine, spark ignition engine kind of things, where you can consider as a premix, and the afterburner engine people consider it as to be a premix flame, although need not to be, unless otherwise the spray are quite fine, right. But generally it is being modeled as a a premix flame, whenever they want to model afterburner jet engines. But whereas the actual combustors or the main combustors, you cannot really model with the premix flame, unless otherwise you have designed a premix combustor, which is being going on today nowadays in order to overcome the problem of emission, right. How to characterize the premix flame then is a very important question. How to characterize it, and which we will be discussing about, that is basically you would need to look at the burning velocities. What do you mean by burning velocities? We will be learning about it. And so, classification of premix flame can be broadly into two categories based on the what is the speed of burning velocity. It can be speed of it can be more than the speed of sound, it can be less than the speed of sound, and if it is more than the speed of sound, we call it as a detonation, and if it is less than that of the speed of sound, we call it as a detonation. So, therefore, detonation, in case of detonation, combustion of traveling at a supersonic speed, right, that is detonation. And whereas deflagration, like where the combustion wave will be traveling at a subsonic speed, right. So, we will be basically concentrating on the deflagration. However, maybe in the next lecture we will be discussing and finding out what is the difference between the detonation and deflagration, and look at a combustion wave, because like your shock wave, the combustion is also considered is like a wave, right. So, how to analyze that, and what are the regime when we will be talking about detonation, deflagration, other things, then I will move into the premix flame. So, with this I will stop over. Do you have any question to be asked or any doubts you are having?